All right, so welcome everybody to the summer bootcamp session on clustering unsupervised machine learning algorithms. So let's get started. So my name is Shahina Raman and I am an instructional assistant professor at Texas A&M University. I do teach introductory courses on data science and machine learning with Python and R, and my research interest is on clustering algorithms. So that is something which is close to my heart, and so I would love to share the fascinating working principles of clusterings to you guys. Now, so before I start, I would like to talk about a famous machine learning scientist called Bernard Shulkoff, and he noted that the world is full of intelligent systems. And these systems display interesting behavior. For example, that we can see all the systems around us, like fraud detections and the credit card transaction systems like, in healthcare, where they measure our blood pressures, temperature, everything. So these are all our intelligent systems which can measure something. And then it becomes more intelligent when they decide something for us. Okay, so this whole transition from measurement to decision is where we are going to play around, and which is called machine learning area. So life with machine learning has become very common, and we know that we are sitting nowadays more at home, and so we have things like Amazon which will order for us. So it doesn't only give us service, but it also gives us suggestions given on the basis of what our history of buying products are. So it constantly adaptive to our own characteristics. So it is learning our behavior. So they also adapt the prices of the product, which varies on how much that product is on demand. And then they also do customer segmentation on the basis of that, what is their buying history, what are the things that they have been interested on. So they give the recommendation according to it. So these are all transitioning from service to decision on what products really we like. And then Uber is something that we all take. And so it's decided on the basis of, they give you suggestions on the drops. They give us a kind of accurate dropper pickup places. And this accuracy of pickup places is also based on certain kind of machine learning. And then also they allocate the bookings based on time, distance, and of course they're also adapting the prices and ratings as well. So life without machine learning is something that we cannot imagine right now, because we can't be using the best search engine, and we won't be able to do all those Facebook taggings and where we are. We can be using the Google Maps for driving somewhere. So we have to understand that what has been the journey of the humankind in the terms of the journey of building a machine for doing simple calculation to another machine which is doing some kind of work and jobs which used to be done by humans. So the machine has to be as much intelligent as a human being can be. So I will go for a quick history. So the question is that we do have intelligent systems, as we see. So the question is that what are the organizing principles that underlie these intelligent behaviors? One such strong contender for this organizing principle behind this intelligent behavior of the systems is called learning. So in 1958, so let's go back almost 50 years ahead, New York Times reported a new machine called the perceptron was created by Frank Rosenblatt, and this guy is on the right, is a psychologist. He demonstrated that perceptron could learn from human experience. Then he recognized later that the perceptron could learn from people. They can instantly translate spoken language. So they are doing heavy works. So this is the time it was attempted to build something like a synthetic brain. So the computer is no longer used only for computing heavy computations, but it is something to do more, like deciding as a human being. Now, at the same time, another revolution was happening. Computers could do more than computations. So they could recognize symbols and hence the patterns, and that gave birth to the computer science as we know it today. So now computers will be capable of doing many things that human can do. And one of these things that things by which these machines can become smart and intelligent is by the process of learning. So what are these different kind of learning that the machine does? So one is called supervised learning. One other is unsupervised learning. Another one is reinforcement learning. So today we are going to focus only on this particular type of learning, which is unsupervised learning right now. And so, and what is the difference between supervised and unsupervised learning? So I think you guys know it already, but I just like to give a quick review. So in supervised learning, so we try to classify some objects or some items or anything in your hand. So we try to classify certain objects into certain groups with the help of already developed label data. So that means that we have some kind of data which have some label, versus unsupervised data where the data comes without any kind of label. So in the supervised context, we do have the notion of training data sets. So we use training data sets, and the training data contains label. And now once they contains label, we ask the algorithm to learn it. So they learn from the training data, and then they classify the future test data. Okay, so they classify the test data and they classify them with new labels, On the contrary, in the unsupervised learning, there is no concept of training data. So there is no data. So there is only one data, okay? In this data, the algorithm itself should be classifying this data or cluster. So we call this as we cluster or classify with new labels. Okay, so there is no console, so there is no training data. So it is even more, so this is much more harder problem because we do not have any information. It's almost like babies. Like the babies, they try to learn what is the right thing and the wrong thing. So we train them and then they do, then they decide whether this is an apple or orange. So but for clustering and unsupervised, babies are the one who has to know what is apple and orange just by looking at it. Okay. So clustering, so let's start with the definition. So now since we are getting into the working principles of these smart algorithms, so what they are actually doing. So they discover the natural groups, and since they're discovering natural groups, so they are completely unsupervised babies. So that means there is no parent over these algorithms to understand what is an orange and what is a apple. So they have to discover the apple. They have to discover the differentiation between apples and oranges just by themselves. So they have to discover the natural groups which can be visible by them, not by human eyes, automatically in the unlabeled data. How? So the objects in the same group should be as similar as possible, and objects in the different group should be as different as possible. Now this is a very so this is a very generic statement that similar objects should be in the same group. Now, the question is that how do we define the similarity? How do we define the similarity? So do we define similar in terms of looks, or we define similar in terms of the characteristics, or by their hobbies, or what? So how do we define similarities? So that is a perennial difficult question, because as you define similarity in a different way, you will find different set of groups. So I might be similar with you with respect to probably age group, but I might not be similar to you with respect to ethnicity. So as you define similarity, you will get different groups. So it's a very, very important thing that we should be deciding from before what similarity measure that we are going to give to these clustering algorithms. So that is called yield-post problem of clustering. Now let's say that we have this input data, okay? So let's say that I give you this data set. Now from this data set, you should be able to find how many clusters are there. So I generally ask this question in an open class, and I think I cannot get your reply over here unless you give me a reply in the chat window. How many clusters do you see immediately? So immediately probably you say me 4, right?
Yeah, 4.
So that, right? Okay, so thanks, Zachary. What about rest? Do you see any more? Anybody else?
2.
So you see 2? Okay, so let's see. So here is it. So there is, in all total, there are 7 clusters. So if you really, really want to be very specific, you can actually write 7. Yeah. So now the thing is that there is no best clustering algorithms for the reason that finding clusters is very subjective and depends on your definition of similarity. For example, some people might like to say that there are only 2 groups. Some people might like to say there are 4 groups. And if some people like to be even more specific, they find subgroups inside each of the groups and they will define them as different groups. So then clustering method is in the eye of the beholder. And these are the easy problem because these are only in 2-dimensional problems. So we can see these clusters, so we will be able to find clusters very easily. But in real life, we do not only deal with 2-dimensional data. We deal with many, many, many higher dimensional data where we'll not be able to see from our human eyes. And that is when the machine surpasses the human ability to see clustering algorithms. So that is why it is important to teach the algorithms how to find clusters in a much more complicated and complex problem, especially in higher dimension. So now we see that clustering is very much dependent on what similarity you are going to impose on the algorithm. So depending on the similarity which has been fed to the algorithm, it will find that kind of clusters, okay? So now we'll start with the most important and very popular clustering algorithms, which is called k-means. The name k is coming from the number of clusters. So this is a number of clusters. And means is coming from how many centers we are going to allow this algorithm to find. So the goal of this algorithm, so the goal of this algorithm is to find exactly k clusters, and the clusters will be centered around its mean, okay? So for example, like you see the data on the left, and you can visibly see 3 clusters in 2-dimensional. So now what k-mean clustering goal is to find the cluster centers. So let's see, this is center 1, center 2, and then center 3. So they will try to find these cluster centers, and then they define a spherical clusters around the centers, and then they're going to define those clusters. And now this cluster will find how many cluster you're going to feeding it. So the tuning parameter in this algorithm is k. So this is also known as the tuning parameter. So if you feed the algorithm with k equals to 3, then it will find 3 centers. If you feed this algorithm with k equals to 2, it will only find 2 clusters, and similarly, like that, okay? So that is the nature and characteristic of the k-means algorithm. Now, what is k-means algorithm similarity defined as? K-means similarity is defined as it will try to find that clusters, which clusters can minimize the inter-cluster distance. So this is defined by the distance, and this is a square distance, or this is also known as Euclidean distance. So what k-means is trying to do is minimizing this Euclidean distance. So that means that it will first try to find those centers from which, and again, the center depends on what kind of K you're feeding. So let's say that you're feeding K equals to 3, and then it will find the best 3 centers from which it will minimize the interclass distance. Okay, so let's say that if this is my cluster center, it will, it is going to find this as a cluster mean because it is minimizing the distance from all the members from its own group. It will not try to find this as cluster center or this as cluster center, this as cluster center, because this cluster center is not minimizing the distance from all of its cluster centers. So this is the similarity index, is that K-means is trying to minimize the Euclidean distance or the interclass or the within class distance given the number of clusters you're feeding. So the tuning parameters over here is the number of clusters. And the characteristic of the K-means algorithm is that it always search for equal size and spherical cluster. So that means that if you have some bigger clusters in your data and some smaller clusters, K-means is probably not a good clustering algorithm. Or if the clusters do not have a spherical shape or a circular shape in 2D, then it probably is not a good clustering algorithm. And we will show that in Python. And K-means is also very much insensitive to the initialization because all this algorithms is very much iterative. And because of minimizing this huge function, it's a sum over the Euclidean distance over so many samples, it has got so many local modes. And so whatever your initialization will be, it probably stuck to one of those local modes instead of. So that means that, so what happens that if you feed this input data in step 1, so you start with some kind of random initialization, okay? So these are, let's say this is your first initialization, this is your second initialization, and third. So let's say you set K equals to 3 and you initialize step. Okay, so this is your initializing step. So you initialize with 3 random numbers. Then what or iteration will do, it will slowly it will take this mean to its center. It will slowly take this mean to its center. So it will slowly take it to the center iteratively so that it will ultimately it will converge after, let's say, after 100 iterations or say some iterations. Okay, so that will be your final clustering. So when the clustering centers do not change anymore, so that's when the algorithm knows that he has found a solution. If it is still changing after iteration, that means that it hasn't found the solutions yet. So usually we take many iterations so that we know that it converges. So let's code now. So I'm going to use the Python Jupyter notebook, and also Alison has also shared that in a Google Documents, which are on your chat windows. So let's open, let me first go to my chat. So I'll show you the different clustering algorithms. So this is my first, I'm working on Jupyter Notebook, and I am using the necessary libraries from scikit-learn, and I'm using the data sets for creating some synthetic data, and then I'm importing the clusters to find all those clustering algorithms, okay? So this is something that I will run first so that I will call all the necessary libraries and functions. So now I will generate some toy data set. So let's say that I generate this data set. So it's a 2D data set, again, it's toy, and you see that I generate 2 clusters over here. So how I did it, I used the make classification function, and I had 200 samples, and I defined number of classes as 2. And then I have some more features over here. All right. So then the first thing that I would like to do is that I always standardize my data. So that means what I do is that I try to center and scale my data so that each of the column of my data has center 0 and standard deviation equals to 1. And then I just plotted it. So the first thing that I would like to do is k-means algorithm. So I import k-means from scikit-learn cluster. So I import this. When I do import, that means I can now use k-means as it is. If I do not have imported it, I have to use cluster dot k-means, and dot usually define a function or a method which like tag alongs the particular library. So now, I use k-means with my tuning parameter, which is the number of clusters which I have to define here. So now I'll first start with, like, let's say I start with 3 because I'm not supposed to know how many. And then initialization, you can start with 1 or 10. So this means that you're starting with 100 different initialization, okay? And then k-means is going to choose which initialization gave you the convergence faster. So, and the initializations are all random. You can choose to be not random if you have some idea, but I have no idea, let's say, and so I choose random. So then I will fit the data with k-means, and then I run this. So you see that we get 3 colors, which means my clustering algorithm, since I told k-means to find 3 clusters, it is finding 3 clusters. And this blob, this yellow blob, is giving the center mean, the centroids, which I told you. So you can also, and you see that if I change to lower init number and run it again, it will give me 3, and it will give me it will give me even worse, because here the blue and the yellow, the blue and the red cluster, they're already merged. So that's why it's always good to have many different initializations, so that k-means will have the liberty to choose and to convert from which initialization the k-means converge. And k-means is extremely sensitive to the initialization. So now let's make it 2. Okay, so it's almost perfect. That whenever we give the 2. So you see that k-means is very much sensitive to the number of clusters you are choosing over here. All right, so now let's go to our second. Okay, so the next one is Gaussian mixture model. So this is much more flexible than k-means. So as I told you that k-means can only find only spherical and all equal size data sets. So unless you give it really the right cluster number. If you do not give right cluster number, it tried to divide the data into equal clusters and all spherical clusters. So what Gaussian mixture model does, it's much more flexible. So it not only finds spherical, but it also finds ellipsoidal or hyperellipsoidal if it goes beyond 2-dimensional. So that's and also Gaussian mixture model can find the cluster by itself. If you give some kind of penalty on it, some AIC or BIC penalty, it can identify the clusters by itself, unlike the k-means. And also the cluster assignments are soft. Why? Because in the Gaussian mixture model is based on distribution. So it will tell you that this object belongs to certain cluster, let's say cluster 1, with some probability. Okay, let's say probability 0.8, and to cluster 2 with probability 0.2. So this means it's a soft assignment. That means it's also opening up the chance that object could be in other clusters, but with some probability, with lower probability. Unlike in k-means, the assignments are extremely hard. So at the end, k-means is going to tell you whether this object is in the cluster or not. So it's a very binary 1 or 0 hard assignment. Unlike the Gaussian, it will give you some probability, which is like a very soft assignment. Okay, so the different kind of clusters that can be found from GMM is these are the different models which you can find in the Python. So this is defined by the covariance matrix. So the Gaussian distribution is defined by the mean and the variance. Similarly, the multivariate version is defined by the mean and the covariance matrix. So depending on the covariance matrix, what you choose, you will have such flexibility of finding the type of cluster. So if you have like So let's go to our Python notebook again. So you can see that I imported a Gaussian mixture from scikit-learn from mixture, and then I gave a n component 3. You can also add, when you add penalty, you might not need to give this component. It will automatically find the number of clusters. And let's run that. So for 3 clusters, you see that it's separated out the smaller one, and it also gives the ellipsoidal one. It is finding the ellipsoidal one. Let's make it 2. And then you can find probably these 2 clusters again, okay? All right, so the next one is the spectral clustering, and I think this is one of the most widely used clustering algorithms because of the fact that spectral clustering do not assume any particular shape for the clusters. So the clusters can come in spherical, ellipsoidal, in square, in triangles, in any form. So it's much more flexible than Gaussian and k-means. So what the spectral graph-based clustering does is that it tries to connect each and every pair of objects. So let's say each of the circles, they are like your A, B, C, D, E, F, G. So these are your objects that you want to cluster. So spectral graph-based clustering, they find all possible connections within these objects, and then they try to minimize the connection between the groups. So they will minimize this. So let's say this is one group. So let's say this is one group, and let's say this is the next group. So what the spectral clustering will do is that they try to minimize this connection. So they try to minimize this connection. So this is the objective function, that they minimize this number of connection. Now this connection depends on the choice of the neighborhood. So however you define the neighborhood, which is like whether you will define the neighborhood by Euclidean distance or by some other distance, or by, you know, or by the angle between 2 objects. So whatever way you're going to choose your neighborhood and the number of clusters, you have to define the tuning parameters. Again, they will give you the certain kind of clusters. So now let's run this one again. Okay, so I use the spectral clustering from the scikit-learn clusters, and I am running that. I'm using, let's say, the number of clusters to be 3, and I have to give them what kind of eigenvalue solver that I have to use, and also I give them the what kind of neighbors that I am using. So it is called the nearest neighbors, and then I'm going to fit it. So again, it's giving me more clusters than before, and then again, if I give 2, it will give me the right number of clusters. Okay, so you see that all these 3 algorithms, it kind of depends on the number of clusters. Okay, now the next one is a hierarchical clustering. So hierarchical clustering is, again, it is independent of what kind of shape the clusterings algorithm clusters have. It doesn't depend on whether the clusters are spherical or square or anything. So these are basically nested clusters. So what the hierarchical clustering doing is that it's like a bottom-up approach. So let's say that these are your objects. So the step number 1 is that you treat each of the objects as its own cluster, okay? And then in all the steps, you start merging these objects. And how do you merge them? Now you merge them with some kind of link. You can use average link or you can use word link. So that is also defining as the tuning parameter of the hierarchical cluster. And also again, you have to define how many number of clusters you want to find. Okay, so now you start with all the objects as its own clusters, and the next step is to merge them. So now looking by this picture, you will be merging P1 and P2 because they are close. You will be merging P5 and P6. Let's say they are just by the distance close. So these are your first step. So in the first step, you only merge P1, P2, and P5, P6. Now, once they merge, so now you define them as one cluster. in the second step. So these are now one cluster. Now in the second step, you will merge again. So who you will merge? You will merge again the one who is closer to each other. So now you will merge from this entire cluster to this, because P naught is close to P1, P2 cluster. We'll merge them. Now again, how do you merge a cluster of 2 with a cluster of 1? So now it comes how you define the link. So average link is that you define the distance between P1, P naught, and P2, P naught, and take the maximum of that. So that is called the max link. And if you don't take max, you can take just simply average of these distance. You take average of the distance between 2 clusters, then see that which one is the closest. So then you start merging them up. And the word link is that instead of looking at the average, what you will do is that you will look at the variance of the clusters. So that means that if you merge these 2 clusters, which means that suppose that if you merge these 2 clusters, these two clusters will have less variance or less spread than merging these 2. Okay, so if you merge these 2, this will be a bigger cluster. So of course, bigger cluster means higher variance. So you will be merging the clusters which are of lower variance. Okay, so now let's go to, again, the Python notebook. Right, so I got the agglomerative clustering, which is the hierarchical clustering, and I used WOD and also the average. So I used the linkage, I WOD, and then I use the number of clusters, how many clusters I have to find, and I use average linkage and the number of clusters to find the average linkage as well. So now I'll quickly run and find this cluster. So again, so in the average fit, you see that WOD has found the cluster, but somehow the average fit, it did not find the cluster. And that's okay. Not all the algorithms are supposed to work for every situations. That is the thing that we should learn, that which one will work and which one will not. Okay, so the next, so you see that all this clustering, they all need to get specified that how many clusters that you need to input. So of course that we want some more automated algorithms where we do not have to specify from before how many clusters that we want to see. We just let the algorithm find for us. So some such algorithms which do that are called mean shift, DB scan, and affinity propagation. So let's quickly go ahead that what they actually do. I'll just quickly show you what they're doing. So these are clustering algorithms. They are basically non-parametric. So here the specification of number of clusters is not actually required. So what they're doing? So what they're doing is that they're randomly starting from any point. Let's say they randomly start from point this. This is a random point. Then what they're doing is that this algorithm is putting a circle of a certain radius around it. And it is calculating the number of points in that neighborhood inside the circle. And then if the number of points is beyond, let's say 4, some minimum point, then they're assigning all the points in the same clusters. Okay, so then after they're done with this, then they shift to the next point, and then they draw a circle again. And then if they find the number of points in that circle more than minimum point, then they again assign to the same cluster as before. So now the whole point is that if you can find a path from which this point and this point is connected, then they all become the same clusters. Now, what's happening here? So suppose that it goes from here to this cluster and is bringing a circle of the same radius. So of course, this does not satisfy the minimum point, let's say 4. So the number of points in this radius is less than 4. So then this point gets disconnected with the rest of the points, and hence it is not included in the red cluster anymore. Okay, So now suppose that again the algorithm randomly starts from a point from here, and then of course if you make a circle, then you will get this cluster. So this is called cluster based on where the densities are. So you know that if things are dense, you will find more and more points. If the things are not dense, that you will do not find any points. So the whole point is that in this case, you will just let the algorithm start with some random points and find the maximum density. And given the two tuning parameters you need to use, you need to tell the algorithm what should be the radius of that circle, and then how many minimum number of points do you expect in that circle. And rest, any arbitrary shaped clusters can be detected arbitrarily. So let's go into the Python notebook again. So here, so we do the DB scan. Here I did the epsilon to be 0.5, and I took the minimum points to be 5, and these are actually default values in the Python. You can also change it, and you run the algorithm. So here you see that the DB scan is finding more number of clusters than expected. So we haven't actually specified any number of clusters. So it actually found 1, 2, 3, 4 clusters by the number of different colors we have. Similarly, mean shift clusters is another similarly density-based clustering algorithm. So if you run it, and it is finding exactly 2 clusters without even giving the number of clusters over here. So mean shift is pretty good for these data sets over here again. And the last is affinity propagation, which and also you do not require to set the number of clusters. All you need is some tuning parameter. And you can also play with this tuning parameter, let's say 0.5, and you see that depending on this tuning parameter, things will also change. Similarly for the DB scan, if you change this epsilon to be, let's say 1 or something, things will change like that. So you should be very much careful about using tuning parameter. It comes with experiences. And also there are some methods where you can estimate it. For example, in mean shift clustering algorithm, the tuning parameter is done by already some kind of estimation function. So they can estimate this tuning parameter given the data, and then they're using the best optimal tuning parameter to find the clusters. And hence the clustering algorithm is, I would say, the best in all this lot, where you do not have to, your data finds the optimal number of clusters without specifying the number of clusters. Okay, so this is the whole thing, and I'm going to show you the overall performance for different complex data sets for all these clustering algorithms. So I'm going to run this very cool data sets where I can show you different kind of data sets over here, and I'll show you how this different kind of algorithms are performing. So you see, these are all different kind of data. So these are all this is isotropic data, where you have equal size of clusters and an equal shape. And you also have an isotropic, that means that you have some circular, some ellipsoidal, so different kind of data. And this is lastly, you have very homogenized data where you have only one set. Still, some of these clustering algorithms, they can find it. So you see that the k-means, Gaussian mixture, spectral clustering, WOD and agglomerative, they all need specification of clusters. But dbScan, mean shift, they don't need it. So let's see how they perform. So dbScan is overestimating the clusters for the first one, but for the next one, they actually found really good, with unlike k-means. And then here, in this third data set, they are overestimating dbScan again, but mean shift is pretty good. But however, mean shift could not find these two circles. So the best one is spectral clustering over here. And you can see that the spectral clustering is almost finding all the clusters, except in the last one, because we are specifying how many clusters they will do it. So the k-means and Gaussian mixture are able to find elliptical or the spherical kind of clusters, as you can see, for the elliptical, for the fourth, fifth, and also for the third data sets, k-means does pretty good. However, for these kind of complex data sets, spectral clustering is still performing the best, and also a little bit of dbScan. dbScan overestimates. All right. So now this is for the 2D data sets. The next problem is that what happens when we have high dimensional data. So let's go to our the next one. So the high dimensional data things becomes a little bit more complicated. So what we will do is that we first try to reduce the dimension and project the real data into some lower dimensional space or subspace or embedding. And then we try to visualize the cluster inside the data and then apply the usual standard techniques of clustering. Okay, so let's start with the iris data, which is a very popular data sets. And let's load that one. And let's find the cluster labels. So there are 3 cluster labels over here, and let's plot it. Okay, so if I plot it, there are 3 different colors, but it's not very apparent because you can see the red one is okayly separated, but the black and the orange one, they are not at all separated when we plot the data itself. Okay, so now it comes into the thing is that now what we want to do is that we want to project this high dimensional data so into another dimension where we can actually see certain features of data. So one such dimension reduction technique is called PCA. So first of all, it reduces the dimension, and how it is reducing, it is projecting the data into those axes, which axis captures the highest variance in the data. So let's just do this PCA component. Okay, so I did use the PCA function from the decomposition, from the scikit-learn decomposition. And what I did is that I did a reduced version of X, and then I'm plotting the reduced version of X on 2-dimension. And you see that the PCA, projecting the data on PCA components, shows much more separatability between the groups than on the original data. So you see for the high dimensions, sometimes, not always, sometimes it is much more useful to see the data or to project the data in a much more lower dimension. Now, talking about is PCA is a linear transformation or linear dimension reduction. We do not want to go only on the linear dimension reduction. So we want to do something more sophisticated, let's say nonlinear. So kernel is much more flexible, but it needs some kind of, you need to specify what kernel that you want to use. And you also need to specify some tuning parameter because you're using kernel, which is non-parametric. So this is a nonlinear dimension reduction, unlike the PCA. So let's see. So this is projecting the data into this format. So you see it is different from the linear, but still you can see the 3 different clusters are well separated over here. Lastly, I want to show you is another manifold-based nonlinear dimension reduction, which is called TSNE, which is based on the stochastic neighborhood embedding. And you can use the scikit function manifold, and you can draw TSNE from here, where you have to specify how many components, like PCA, that you want to throw the data into. So let's say we want to throw into only, you don't have to be so crazy, and you have to initialize it, because again, this is an iterative process. So you can initialize it with random things or whatever you want. You can, and you have to use a tuning parameter, which is called perplexity. And that is, I have set it at 30. And you can change it. So let's see, let's play around with this. So you see, so this is for 30, and again, you see the data are well separated than the original one. The original one is crazily bad. So, so now if you change it to 10, what happens? Okay, so you change to 10, so you see that it's the data are again well separated. And if you change it to, like, let's say 100, what happens? Okay, so it's again, if when it to 100, it's almost like PCA. It's giving very much similar to what PCA give. Okay, so you see that PCA can be a special form of a special case of TSNE with a certain. Okay, all right. So now what we are going to do is that now choosing this perplexity is a different question altogether. So it depends. So these are very sensitive to what kind of perplexity you tuning parameter you want to choose. So sometimes it depends on your experience with the data. Sometimes you need the domain knowledge. Sometimes there are methods like estimating this perplexity tuning parameters. If available, you can use it, but it doesn't guarantee that you always going to have the best solution. Okay. So now what I'm going to do is that once you have reduced the dimension reduction, now you apply k-means on this on these data sets. Okay, so let's start with applying k-means on the original X. Let's see what you get. So this is, I give, let's say I give like 1 or 10 iterations or 100 iterations. It's always good to give. Okay, so this is what is you're getting. So still the green and the orange, they are mixed up. It's and you don't like to have clusters like this. It's not very well separated. Now let's apply k-means on X projected on PCA, which is a linear dimension reduction. Okay, so you see this is the original one, and this is so this is the PCA. Okay, so you see that it's much more separated than here. So you see, with respect to the original one, this one is much more separated. So let me change this to X, and let me rerun this one. Okay, so you see this is the first one is clustering on PCA, and second one clustering on the original X. So you see that the clustering is much more better on PCA. I'm not saying that PCA will work every time, so you need to use other dimension reduction as well. So I'm going to do also k-means applied on TSNE, and let's see what it gives. Okay, so let's run this one. Okay, so since it's almost a similar one, but still it is better than doing k-means on the original X. Okay, now let's change it to a little bit better perplexity. I don't want to use that 100. Let's see, you use a perplexity 50. Okay, so this is you see this much more well clustered and well separated. And so that means it is much more easier to find clusters on TSNE rather than on here. So you see the clusters are accordingly to it. Okay, I think, so I'm going back to my slides to give my ending notes. And I'm sorry for doing this to and fro between iPads and my Python notebook. So in high dimensional, the first technique is that project the data X on a reduced dimension and then apply the standard clustering technique. So I just showed using the k-means. You can use dbScan, you can use Gaussian mixture, you can use spectral clustering, graph clustering, or anything that you have in your hand and do it. And the thing is that do not only try on PCA, try other nonlinear dimension reduction techniques as well, especially like kernel PCA or TSNE, which is much more robust. And PCA is a special case of TSNE, so you will never going to lose on any information. So now where do we stand after 50 years? So 50 years of research and clustering, intelligent, smart clustering algorithms. Following the great professor in computer science, A.K. Jain, said that despite these developments, there is no single algorithm which has emerged to displace the k-means scheme and its variance uniformly. And that was published in the Proceedings of National Academy of Science in 2017. So that's where we are. So which means that computer still needs us. And so we still need to keep our researchers on and keep our eyes open. I hope this has helped you in understanding the clustering unsupervised algorithm. And I'm ready to take any questions from you.
All right, so that was awesome. So I've been following the chat, and we got a couple of questions from chat. So we'll start off with those, and then we'll kind of open the floor up if anyone wants to say anything as well. So Rohan asks, what is the affinity in spectral clustering? You were on like slide 20, if that helps with context.
Yeah, sure. So the affinity is a great question. So you know, affinity means closeness. So the affinity defines to be how close and similar these elements are. So for example, that it depends that if you define affinity as 1 over, so you, oh, I'm sorry, I have to scale the screen. So let's see, we are here. Okay, sorry for that. So my iPad is not coming. Yes, so here. So affinity means closeness. So we want to define the affinity between, let's say, D and F points as 1 over distance between D and F. So less the distance is, more the affinity is. That makes sense? So, and you can define distance by Euclidean distance, by Manhattan distance, or any other norm that you want to, or maximum distance, or any other distance that you want to define at.
All right. So, and Zachary asks, what are the AIC/BIC penalties for excessive number of clusters? That's slide 17.
Yes. What other aspects of? Can you repeat the question?
What are the AIC/BIC penalties?
Oh, that's a great question. Actually, I wanted to cover that, but there's a lack of time. So here is the thing: is that as you can see that in Gaussian model, you have to specify the number of clusters. I don't want to do that. So what you can do is that you can ask the algorithm to find it by itself. So AIC and BIC penalty is that not only it is so if I just write the Gaussian model, so it is like e to the power half x minus some mu given by some sigma square or something like that. So it is not only maximizing this, but I'm maximizing some kind of penalty on k. Okay, and now the version of penalty k, if this is exactly equals to number of clusters multiplied by number of samples, that's going to be my AIC, and BIC is number of cluster multiplied log of number of samples, and that is called BIC. So depending on the type of penalty you use, and then you maximize this entire function without specifying the number of clusters. So let the algorithm maximize it itself and find the true number of clusters.
All right, great. So, and then another question from Rohan is, for the number of initializations and k-means, does it mean that the higher number of initializations means more accurate in the clustering mean, or does the clustering mean starts to be indifferent to the number of initializations at a certain point?
So here is a rule. Higher the number of initialization is, your results will be better. Okay. The reason that we cannot choose really many because of the time constraint, but if you do not have time constraint and if your machine is good, you can actually like take initializing to be like 10,000 and find the right kind of right clustering.
Right. And then I think the last question we got from the chat is from Tushar. He asked, is there a way to use a different metric in this algorithm, the k-means algorithm? I think it was on slide 12.
Absolutely. That's a great question. So exactly, k-means, you can always code it. You will not definitely write it k-means, okay? So for example, this is Euclidean distance or square distance. So, and mean and square distance is always minimized at means. Okay, so if you minimize the square distance, it will minimize at means. Let's say you take a L1 norm. So let's say you take a more absolute norm. Okay, so if you take an absolute norm, that means that you can redefine your objective function to be not a square function, but an absolute norm. Then if you minimize this, then your centers will be, you have any idea what it will be? The centers will be the median. Okay, so then it will be a k, it is defined as k-medioid algorithm. Okay, you can change to any distance you like, but then it will not be k-means anymore, because k-means is always related to square distance. And if you use different distance, then it will be k something else. That makes sense?
Awesome. So we're around 4 minutes away from the end. I think that was an awesome talk. I think a lot of us would agree. We really appreciate you coming on, Shahina. So before you guys all head off, I want you guys to take a survey. I sent the link in the chat. Basically, it can give us feedback into how it went. And of course, Shahina will also take a look at that. And another plug is come to Tama DataCon 2020 in October. We'll have more workshops like this. And so that also means that feedback from the survey would be extra important. So please take our survey. We still have like 4 minutes. So if anyone else has any questions, please feel free.
Yeah, like how are you guys doing? How is quarantine going on? We can talk about that too. We have 4 minutes.
Well, I'm sure everyone agrees that quarantine is pretty crazy, but you said you teach Stat 355. Is that true? And that just talks about a lot more of this stuff?
Oh yeah, I can go into details. Yeah.
Are there any prereqs or can non-stats majors take that?
Yeah, it's absolutely open for non-stat. The prereq is that you should have some coding experiences. It doesn't have to be Python. You can be a Java writer, you can be a C++ writer, or anything. So any coding writing would be very helpful for you to start off, because we'll start on all these algorithms rather than doing all this basic, tutorials. Yeah, that would be the only prerequisite. Otherwise, anyone can do this class.
Well, I'll check that out because this has been really fascinating and I thought you did a great job presenting. Thank you.
Thank you so much. Thank you. I really appreciate it. I hope you learn it, and I hope that you know which one to use, and you know the differences, you know the characteristic of the tuning parameters, and you know also the dimension reduction techniques that you should be using. Just don't use only PCA. There are a bunch of other things that are much more useful as well.
Yeah.
Just wanted to say thank you, Shahina. I thought this was awesome. You did a wonderful job. And I've also taken that course she was talking about, and it's really great. I wish I had taken it with her as my teacher. But yeah, y'all should consider taking her course in the fall too.
Thank you so much, Alison. That's a very nice and very kind comment from you. Yeah, I hope to see some of you guys in future, at least in the real datathon in October.
Yeah, and before I think everyone leaves, we can make sure to get the slides and all the resources on the website and of course a recording will be posted afterwards. So yeah.
All right, well, thank y'all so much. If you are hopping on to another meeting, the links are on that events page, so you can see them there. Thank you, Shahina.
Bye. We wish you all have a nice weekend. And see
You
you
as well.